Hey everyone, welcome to week 11 of mini lecture. Today we'll be talking about P versus NP as well as the idea of NP completeness. So we'll be talking about, difficulty of problems, and in particular we'll be talking about what these letters really mean. So I know that for a lot of you, PNP is on your mind for a variety of different reasons, but I hope that this lecture is going to be interesting to you and hopefully take your mind off of the other PNP that you're thinking of. So let's jump right in. If you remember last week, we talked about reductions, which is essentially saying when one problem can be reduced to another problem and can be solved using the mechanisms of that problem. And afterwards, Neil defined search problems. So if you remember, search problems are this class of problems that deal with searches, I guess. This is not a very good definition, but I guess the defining property, the characteristic that you should remember is that given some instance of a search problem with what problem you're solving and its parameters encoded in this instance I, and given some proposed solution S, I can pass them into some algorithm that checks whether this proposed solution is actually the right answer, or the intended solution for this instance of a problem. So this algorithm is just a checker for whether this is a checker, and it should operate in polynomial time. So loosely speaking, search problems are problems that are easy to check, easy to verify, I guess. This means that you can always, given some proposed solution, you can always verify it efficiently in polynomial time. An example of this that people bring up is Sudoku, right? Let's not talk about how easy or difficult it is to solve Sudoku, but if you're given some proposed solution, if someone hands you a Sudoku and their solution to it, it's fairly easy to check whether that solution is the right one. You just check all the rows and the columns and each grid, whether they have all the numbers 1 to 9. So if you're not familiar with Sudoku, think about, think about factoring. So if I hand you a super large number and I ask you to factor it, let's not talk about how easy or difficult it is to factor, but if I give you a proposed solution that suppose I say I can factor into these numbers A and B, then it's fairly easy to check that whether this factorization is correct. You just multiply them together and see if you get the original number, right? So these problems are easy to verify. And we say that the class NP is a class of problems that consists of all search problems. So this is a fairly straightforward definition. It just says any problem in NP is easy to verify. It's verifiable in a polynomial time algorithm. So then what is P then? P is the, the better brother or the easier brother. It's search problems that have a polynomial time algorithm for solving the problem. So loosely speaking, it means search problems that are easy to solve. So again, I must say that easy to solve, easy to verify, these are defined basically if we have a polynomial time algorithm for doing these things, then it's easy or efficient. All right, so right off the bat, you should notice that P is a subset of NP. Whether this is a proper subset, we don't know. We'll talk about that. So every problem in P is also an NP. I mean, one way to see this is, P is defined as search problems that have some other constraints. So, it's just a part of NP. But another way to say this is, given a problem that's easy to solve, it's also easy to verify, right? Because you can just solve the problem and verify whether it's whether your solution and the proposed solution are identical. All right. So that's the definition of P and NP. And so inevitably, we're going to talk about this question of whether P is equal to NP. This is, the millennial prize problems. You win an obscene amount of money for, writing down whether this is equal or not. But it remains unsolved, and it's one of the most interesting problems in, I guess, computer science and even mathematics today, because there are consequences. There are like serious consequences to this problem. So let's just say, like, suppose P equals NP, then a lot of things will go wrong. For example, let's see. So P equals NP will mean that any problem that's easy to verify is also easy to solve. So for example, that means Sudoku is solved as just as easily as it is to, I don't know, to check whether the answer is correct. And by like as easy as, I just mean there are polynomial algorithms for both. And this is problematic in particular because maybe in CS170 you learned that it's very hard to factor large numbers, but very easy to multiply large numbers. And a lot of our, I guess, cybersecurity protocols rely on the fact that it's really hard to factor large numbers. So in this case, if P is equal to NP, then factoring would be just as easy as multiplication, which means that essentially all your bank accounts would be compromised. That's not a very nice thing. So I think most people would say that P is probably not equal to NP. And there are consequences to that as well. And we'll talk about what the consequences for P is not equal to NP really is. I guess first thing you can notice is that if P is not equal to NP and P is a subset of NP, then that means NP has problems that are not in P, which means NP has problems that are easy to verify but hard to solve. So in the next couple of minutes, we'll talk about what it really means for NP to have harder problems, the hardest problems in NP. Okay, so let's take a slight detour to talk about reductions. If you remember from last week, reduction is a way of talking about how to use algorithms for one problem to solve another one, or reducing problem A to problem B. So a quick recap might be, if I can reduce problem A to problem B, then I can say that given an algorithm for problem B, I can also give an algorithm for problem A. And remember, this whole pre-post processing stuff is essentially if I take an instance of problem A and I have an algorithm for problem B, then I do some pre-processing to turn it into an instance of a problem B. Now I pass it into the problem B algorithm, and then once I pass it out, I get some solution to problem B, and then after post-processing, I get a solution for problem A. So if that just made no sense to you, please go back and watch the previous lecture. I hope that'll be a good enough explanation. But essentially, if you're unfamiliar with reductions, you should definitely go back to see what it is. So let's make this more specific for search problems. So as just a reminder that search problems could have no solution at all, and you should be able, your algorithm for such a search problem should have the ability to identify whether there is an answer at all. So again, we take an instance of problem A, which is the problem we're reducing to problem B, right? And then I pre-process, I turn this into some problem B instance, B algorithm, and then I have two paths coming out. Path one is there is solution. So there is solution. Then I do post-processing, I turn it into a solution for the problem in A. If there is no solution, then I better have that if there's no solution for problem B, then there should be no solution for problem A. Otherwise, our reduction would be in big trouble, right? And then we can say, you know, after I do all this, I can say that this entire box, if I just, you know, encapsulate all of this, this entire box is an algorithm for A. Algorithm for A. And it's like, I don't know, an abstraction where you take a big box and you put it over some smaller boxes and you say, okay, I have a new algorithm that I only care about the input and output for. And input is, you know, instance of A, output is solution or no solution for A. All right, so that's the reduction for search problems. And if you remember, there's a notion of difficulty. And so as just to remind you, difficulty flows along with the arrow. So if A reduces to B, then B is at least as hard as A. So, you know, as you go, I don't know, suppose you have A reduced to B, reduced to C, reduced to D, then difficulty flows from the left to right. So difficulty goes up. And then algorithms flow down, which means the algorithm for D gives the algorithm for C, gives the algorithm for B and A. So algorithms flow down. Yeah, right. This is not my personal favorite way of remembering which way it goes, but I guess, I don't know, I've now provided 3 ways of remembering which is more difficult. Hopefully one of them works for you. All right. So now this gives us a way to talk about what is more difficult than something else. So you can sort of see that, you know, if A is more difficult, if A reduces to B and B reduces to C, then it must be true that A also reduces to C. You just sort of compose these reductions. And you can imagine that, you know, you have these boxes and you just start with another box, and then you box the whole thing up to get from A to C. And you'd be correct. So then essentially this has the consequence that if B is harder than A and C is harder than B, then C is harder than A. Now, think about this. What if I can reduce A to B and I can also reduce B to A? What does that tell me about difficulty? Well, if A reduces to B, then B is at least as difficult as A. If B reduces to A, then A is at least as difficult as B. So essentially we've gotten into a situation where, you know, A is bigger or equal to B and B is also bigger or equal to A. Well then, A must equal to B. So this is sort of the way that we define what it means to be of the same difficulty. So if A reduces to B and B reduces to A, then we say A and B are as difficult as each other. And this is the basis on which we'll build NP completeness. So remember in the past, a couple minutes ago, we said that if P is not equal to NP, then there are problems in NP that are not in P, right? So this means I have, here we go. This means I have problems that are in the circle which denotes NP, and P is a subset of NP, but I have some other stuff in NP, right? And so there's a class of problems called NP complete. And what this means, how we define it, is NP complete. Let's write this here. NP complete means any problem in NP. So given any A in NP, A reduces to B. Okay. If B is in NP complete. So consider this again. Think about this, what this means for our problem B. So if B is an NP complete problem, then for every single A in the NP class, I can reduce A to B, which means that B is at least as difficult as every single NP problem. So B must be among the most difficult problems in NP. It's very surprising that such things even exist, but as we'll see later on, they really do, and we've encountered some of them. For example, 3-SAT. So essentially what this means, you know, is that we define this class of problems NP complete that are at the most difficult level of all the NP problems. So these are the group of problems that are the most difficult out of all the NP problems because everything reduces to them. And it's also worth noting that since, you know, every problem reduces to NP complete problems, that means NP complete problems reduce to each other. So then if I have like X, Y, Z all in the NP complete class, then X reduces to Y, reduces to Z, reduces to X. And now we're just writing letters, but realistically, you'll be dealing with real problems. Like, for example, traveling salesman, set cover, 3-SAT, things like this, like a lot of very concrete problems. And it's a very interesting exercise to think about, you know, how these completely, seemingly unrelated problems really reduce to each other. And that'll come from some clever constructions that Neil is going to talk about. And I'll also say that in the previous week, when we did reductions, we asked the tutor problems that we went through are secretly reductions from NP complete problems to each other. So I encourage you to go back and look at those walkthroughs again to see exactly how these NP complete problems reduce to each other. But for now, let's just recap what we covered today in terms of, you know, what PNP and NP complete problems really are. So we said that, you know, all of this NP complete business comes from the consequence of if P is not equal to NP. If P is not equal to NP, then this little diagram holds that, you know, NP still contains all the P problems right here, right? But then it also contains some problems that are harder than P problems, and we call them NP complete. These are the hardest problems in NP. And then everything above that, everything more complex, is called NP hard. All right. So now if P equals NP, then well, P will be equal to NP, and it'll also be equal to NP complete, because NP complete is just the hardest problems in NP, but if every problem in NP is P, then, you know, the lot of letter talk, but essentially it means that everything is the same circle. And then again, we have NP hard. So this is a very useful diagram to remember. Neil just, I don't know, Neil just gave me this diagram this morning, and it just improved my life quality significantly. And so I guess another way to see this, you should be fairly familiar with this diagram, because in the little penguin thing, whatever this is for the logo of 170, this is actually the exact same diagram, right? Because the P is inside this NP, I guess his body is NP then, or her body, NP, and then you have P nested within this NP class, and then there's NP complete and then NP hard going forward. All right, so that's it for today's first segment of mini lecture, and then in the next segment, I'll pass it off to Neil to go through one of the reduction examples in great detail. So, bye.
Thanks, Lily. In this video, we'll be covering a quick reduction example from Rudrada path to Rudrada cycle. And so if you want more practice or like walkthroughs of reductions, feel free to check out last week's mini lecture. We have a couple of examples of more in-depth reductions. But in this video, I just wanted to keep it a little bit simpler, just to kind of ease you guys into the notion of like of a real reduction, right? So last week, if you remember from the mini lecture video, we covered what Euler paths are as well as Rudrada cycles. So just a quick recap. And the Euler path problem is we want to find a path between two vertices in a graph that contains each edge exactly once. And the Rudrada cycle problem was we want to find a cycle in a graph that visits each vertex exactly once. So again, keep in mind the key differences are in Euler path, we care about in the Euler path, we care about a path, whereas in Rudrada cycle, we care about a cycle. In the Euler path, we care about, you know, traversing through each edge exactly once. In Rudrada cycle, we care about traversing through each vertex exactly once. And again, we saw that the Rudrada cycle was kind of like similar, was very similar to the TSP problem, traveling salesman problem. And so last week I mentioned that the Euler path problem is much easier to solve than the Rudrada cycle problem. And what I mean by easier is there's a very well, you know, there's a known polynomial time algorithm, like an efficient algorithm to solve the Euler path problem. But for the Rudrada cycle problem, there isn't really, you know, a known efficient algorithm to solving it. And so what we covered last week, or actually earlier in this video, Lily covered, you know, P and NP complete and things like that. And so what we'll see is the Rudrada path problem is a hard problem, which means it's NP complete. And so one of the things that I also brought up last week was kind of like, okay, the Rudrada cycle and the Euler path problems seem to be really, really similar, right? There's only like two differences. One's a path, one's a cycle, one's an edge, one's a vertex, right? So what makes Rudrada cycle so much, you know, more challenging to solve? And so in this video, we'll like go over why the first part of it, like the notion of a path versus a cycle, doesn't really affect the complexity of the problem. The main complexity, the main additional complexity that comes about is due to, you know, this edge, you know, caring about edges versus caring about vertices. And so that's why let's compare these two problems, the Rudrada path and the Rudrada cycle. So again, the Rudrada path, the definition of the problem is the exact same as the Rudrada cycle, except replace cycle with path, right? So in the Rudrada path problem, we're trying to find a path from, I don't know, let's say start to end, right? S to T. We're trying to find a path in a graph that visits each vertex exactly once, right? And so we're trying to see, okay, is a Rudrada path problem, okay, we have the Rudrada path problem, we have the Rudrada cycle problem. Is one problem significantly, you know, easier or more challenging to tackle than the other, right? So yeah, let's check it out. So again, to bring up again, we've seen that the Redrata path problem is an NP complete problem. We don't have a known, efficient way of solving it. So moving forward, let's look at the Redrata path problem. So, oops. Okay, this is the, apologies. Okay, so this is the Redrata path problem. Let's say we have like this sample graph, and we're trying to find a path from S to T such that all of the vertices are used exactly once, right? Again, going back to the definition, that's kind of like what the definition of like Redrata path or cycle is. Except instead of cycle, we're looking for a path. So now what's our main goal for this, challenge, right? We're trying to compare, again, our overarching goal is we're trying to compare Redrata path with Redrata cycle. And so how can we like maybe think about the Redrata path in terms of like, how can we maybe convert it into a cycle problem, right? If there's some way, if we figure out like, some way to reduce, make a reduction or something, somehow relate the Redrata path and the Redrata cycle, that will tell us more about which one is maybe a harder problem or whether they're both equally just as challenging to solve. And so the idea that we use in this problem is kind of like a pretty simple addition to the graph, right? So if we copy over the graph here, and in this case, we're trying to, analyze Redrata cycle, right? How can we, relate the two problems? And so again, it seems like, okay, if you want a path from S to T, that's what we want in the Redrata path, but in the Redrata cycle, we want some sort of cycle, right? So why not, like, let's just complete this entire loop, right? So let's maybe add in another node here and connect it just to S and to T. So maybe something like this, and then something like this. And let's call this node X. So what that's kind of doing is, if you think about it, the Redrata path problem would solve like, it would find some sort of like path between here such that each vertex is covered exactly, it's like visited exactly once, and then it would end up at T, right? Now adding this extra node X right here, all that's doing is it's going to ensure that whatever path that we've found from S to T, it's literally just going to complete that path, right? It's going to complete that path all the way around here. Sorry that there are a lot of dotted lines here. Let me try making that more clear. So by introducing this variable X, if you imagine, like, let's say, for example, like we found a Redrata path, right, from S to T. In order to convert it into a cycle, all you would have to do is add this kind of imaginary node X, and then, complete the cycle, right, by adding this edge and then this edge. So the whole point, or even to take it a step further, let's say we started the other way around, right? Instead of starting with a Redrata path, let's say we started with a Redrata cycle problem. And let's say we were given this graph, right? And let's say we found a cycle, we found some Redrata cycle, right? But we want the path from S to T. All you would have to do to make it a Redrata path is just get rid of, again, this edge and then this edge. Then what we're going to be left with is a path from S to T that's also a Redrata path, right? So that was kind of like the main point of this. We're basically reducing from the Redrata path to the Redrata cycle problem. And what I mean by that is this is the reduction that's going on, right? In the beginning, we're given some sort of Redrata path problem, right? I kind of nicknamed Redrata. But anyway, we're given some sort of Redrata path problem, such as this one. What we do next is we add the edges x comma s and x comma t, which is, again, this one and this one. So now we have a new graph, right? If you call this G, you can call this graph G prime. Then what you do is you run the Redrata cycle algorithm on the new graph G prime, right? However you solve Redrata cycle, let's say there is some sort of algorithm to solve it, right? Like hypothetically speaking. So if you have an algorithm to solve for the Rajada cycle of a graph, you kind of chug this new updated G prime graph into it. And so what it's going to give you is some sort of, it's going to give you the Rajada cycle for that path, for that graph, sorry. Now, once you have the Rajada cycle, so I'm just going to say, now you have our cycle on G prime. So you found the Rajada cycle in the kind of like the modified graph, right? G prime. So now, again, our main problem in this reduction is we want to solve for the Rajada path, right? So now, how do you convert from the Rajada cycle back to the Rajada path? All you have to do is get rid of edges xs and xt. And then what you're going to be left with is the Rajada path answer, the answer to your original problem. And so the whole point of this exercise of this reduction is to say that, okay, our whole goal was we wanted to figure out which one of these was harder than the other, or whether there was no difference between the two. And so what this reduction shows is that since we're using the Rajada cycle problem to solve Rajada path, that means we know that Rajada cycle has to be at least as hard as Rajada path. As a Rajada path problem, right? The Rajada cycle problem is not easier. Why? For example, let's assume we had a polynomial time algorithm for the Rajada cycle, right? Let's say hypothetically we had a polynomial time algorithm, right? If you had a polynomial time algorithm for finding a Rajada cycle, that means all you would have to do is plug some sort of Rajada path problem into this reduction, run the polynomial time reduction cycle, Rajada path. Sorry, let me start over. So again, let's assume that you had a polynomial time algorithm for finding a Rajada cycle. That would be a contradiction, right? Because that would mean that you can also solve the Rajada path problem in polynomial time. Why is that? It's because of this reduction, right? If you reduce the Rajada path problem and you use Rajada cycle to solve it, and if Rajada cycle is just a polynomial time algorithm, that would also make the Rajada path problem polynomial time, right? So that means we know Rajada path is NP complete, again, from this table. So that means we know that the Rajada cycle problem must be at least NP complete. There's no way it can be easier than NP complete, right? And just kind of as an exercise for the viewer, you can also perform this reduction the other way around, right? Reduce Rajada cycle to Rajada path, and that way you can show that they're the same. They'll have the same complexity in terms of the difficulty of the problem. So yeah, again, kind of to drive the point home, looking at a proof for this, right? So in order to prove that this reduction actually works, we're going to have to prove it two ways, right? The case one is when the Rajada cycle has an answer, what happens, right? So whenever the Rajada cycle algorithm takes in a graph through this reduction, through this transformation, you have G prime, right? You have your new graph. Whenever Rajada cycle has an answer on that new graph, you can find an answer for the original Rajada path problem, right? Because all you have to do is you just have to delete x comma s and x comma t, and it's just going to give you the Rajada path problem, right? And how do you know this? You know this because if you look at this graph, right, G prime, let me just erase some of this stuff. If you look at G prime, let's say you calculated and you found some sort of Rajada cycle, right? We know a Rajada cycle passes through every vertex exactly once. So once you have a Rajada cycle, that means it passes through x exactly. That means it passes through x exactly once, which means it uses xt and xs exactly once. So if you delete, again, x was kind of like an addition that we added to transform this problem into a Rajada cycle problem. So if you delete x comma t and x comma s, what you're going to be left with is the rest of the cycle, the Rajada cycle, except for those two edges. And that's just going to leave you with a path from S to T that is also a Rudrada path. So that's how you know, like when the Rudrada cycle has an algorithm has an answer on G prime, you will have an answer for G, for the original graph, for the Rudrada path problem. And case 2 is when the Rudrada path problem has an answer, you also know that you would have an answer for the Rudrada cycle problem. This is kind of the other way around, right? Because all you'd have to do is, let's say you have a Rudrada path here. In order to convert it to a Rudrada cycle, all you have to do is kind of like add this extra node X and connect XS and XT. And then you can easily find a Rudrada cycle by literally just adding in those two edges into the path. So that's kind of why it shows, that's kind of like both ways of the proof as to why this reduction works. And there's one last like really important component that a lot of people miss sometimes. And let me just copy that down real quick. So the last component is the actual like runtime for the reduction itself. And so what I mean by that is this step and this step, right? So we need these two steps of like transforming the answer, transforming the problem back and forth. We need those to be, efficient, right? If these transformations themselves are like, I don't know, some like NP complete or NP hard transformation, that's not really going to tell us much about like, how we can reduce the problems, right? Instead, if they're simple, like relatively simple transformations, in this case, it's literally just adding in two edges, we know that our reduction tells us, we know that we can, confidently make the statement that the Rudrada cycle algorithm is at least as hard as a Rudrada path algorithm. So it's a really important component. Anytime you're transforming or reducing a problem to another one, you need to make sure that transforming back and forth is something you can do efficiently. There's an efficient way to do it, right? Usually it's like a linear transformation or just like representing a list as a graph or like kind of like a simple transformation like that. But it's just, I just wanted to go over it for completeness. But yeah, that's kind of like a walkthrough of the Rudrada path to Rudrada cycle problem. So now we know that the Rudrada path problem reduces to the Rudrada cycle problem, and you can show it the other way around too, which means the Rudrada cycle problem is not easier to solve than the Rudrada path problem. Again, if you want more resources for example reduction walkthroughs, check out last week's mini lecture or the textbook section 8.3. Thanks, guys.